Welcome to SingleCrystal 5. In this tutorial, we'll show how you can display your simulated diffraction patterns in 3D, measure reflections and their distances, and isolate layers of reciprocal space. SingleCrystal can take your simulated diffraction pattern, such as this TEM pattern, and simulate a weighted reciprocal lattice in 2 dimensions, where each reciprocal lattice point is sized in proportion to its intensity. We can do the same in 3D using the 3D weighted reciprocal lattice command. You can customize how this looks using the reciprocal lattice group in the inspector. We can set the overall size of reciprocal lattice points using the size slider, but we can also set the relative weighting, how the size of the points maps to their intensities, and this can be done by volume, area, radius. Use the weight slider to map the intensity to a power of the radius, starting with no weighting, going to volume, area, or radius. We can also show this enclosing sphere, which defines the maximum extent of our simulation, but we can turn it off if it gets intrusive. Here we have a set of axial vectors passing through the center of reciprocal space. We can customize these with the axial vectors group, toggling them on or off, editing their colors, styles, and labels. As with simulated 2D patterns, we can set the colouring. Here I'm going to colour by intensity using a rainbow scale. Since this is a 3D pattern, we'll add a bit of rendering to make things clearer. I'll start by adjusting the lighting. Let's turn on all of our spotlights, and we can change the degree of ambient lighting as well. We'll also add some depth fading to enhance the 3D effect. One could use depth fading to rapidly profile blocks of the pattern. We'll start by setting a view direction. Now we'll adjust our depth fading settings so that only a thin sliver of reciprocal lattice perpendicular to the view direction is visible. And the easiest way to do this is via the needle preset. Notice our visibility graph. There's a sharp spike in the visibility midway down, and looking at the diffraction pattern, we have a cross section through reciprocal space. We're back to a 2D pattern here. We can turn on reflection labels to be clear about the orientation. But unlike with a 2D simulation, we can click and drag the depth slider to rapidly profile different levels of reciprocal space. Having too many reflection labels does tend to clutter up the pattern. But we can identify reflections simply by hovering over them with the mouse pointer to display an info tip. For example, like this. We can expand the tip to display more information or show that particular reflection in the reflections list. As with our 2D patterns, double-clicking a reflection in the reflections list highlights the displayed reflection on screen. We can also measure distances and angles between selected reflections, but to do this we require the arrow tool from the tool strip. What we need to do is to shift-click on multiple reflections to show their distances and included angles. And this display can be rotated. To clear the display, simply click outside a reflection. You can make your reciprocal lattice more interesting by adding planes and vectors from the stereogram. To do this, we'll return to the reciprocal lattice group in the simulation inspector, and we'll turn on the planes from stereogram and zone axes from stereogram checkboxes. We'll now edit our stereographic projection. And the easiest way to do that is to expand the mini stereogram, and that brings up our stereogram inspector, and we'll navigate to the poles inspector. Now let's get rid of these existing traces by selecting them and deleting them, and we'll add a new pole parallel to the 111 lattice vector. Let's display its trace, and let's set the trace angle to 45 degrees. Let's set that colour to magenta. There we can see that in the 3D display. This is a small circle on the stereogram and a cone in reciprocal space. And we'll add the trace of the plane 001 to the stereogram by clicking the add button and adding 001, and this will be a plane normal. Let's set this to blue, and let's show its trace with the angle of 90 degrees. We'll now minimize the stereogram so we can focus on the 3D display, and let's turn off these labels. So we now have a 3D weighted reciprocal lattice that is colored by intensity and shows a custom zone axis and the 3D equivalents of a 45-degree small circle and a great circle, which is our blue trace of the 001 plane. We hope you find this useful and a new way of looking at diffraction data in 3D.